Hi everyone, my name is Chris Helm, and this week we are putting together everything we've done for the last 4 weeks into a single project. So rather than create something brand new, I've extended and reworked one of the projects that we did in the past, the bee project specifically. So if you remember the bees from 2 weeks ago, they were sense-driven AI. So except for a few edge cases, all of their behavior was driven by what they could see, what they could hear, and what they touched. So this week, I've extended that so that we have some finite state machines that are more refined to allow better control over the bees. And I've also introduced hierarchal state machines. So each bee has 3 finite state machines attached to it, and based on game conditions, the specific finite state machine will change. So they'll have their default behavior, but if they go to panic, instead of including the panic functionality in the default in the default script like we did last time, this time the panic functionality is its own finite state machine. And then I've also introduced a day-night cycle into the game, which is controlled by a finite state machine run by the game manager, so that at nighttime, the bees can have another behavior where they go to sleep. The last thing that I added was A-star pathfinding. Instead of using Unity's nav mesh like we did last time, we are using our own nav mesh. So just to show you how that works, we'll go ahead and press play here. Now I have the spacing set pretty wide just for this small part right here. I'll knock it back down to where it needs to be for the demonstration after this. But you notice that the navigation structure itself is generated as soon as the game starts. And then if we come over here, we can punch in a couple of random numbers. So you can see there's the A-star algorithm. It's not it isn't the shortest path, but it is a path. And then you can also see, if we come down here, I've also optimized this so that when it updates, it won't slow anything down. So each node, it only updates traversable nodes in batches, and then it will pause and wait for a short time before it updates the next ones. And I'll show you how that works in code when we get there. So let's go ahead and shut this down, and I will knock this back down to what it needs to be. We'll turn the game manager on, and we will press play. Now, in order to avoid the game freezing, I have the player and all of the bees set to a delay to allow the navigation to be fully generated before they start running. So here in just a second, since I set the day-night cycle down so low, you're going to see it just turned nighttime, so all of the bees are going to go to sleep now. Just like last time, the player can gather these flowers and plant them if he has any in their inventory. There's also a panic button, which I will illustrate right now. So if we push the panic button, I've also modified this to take advantage of the pathfinding structure so that the bees don't line up like they did last time. So I added the sleep functionality because I was trying to add a win condition that required the player to get all of the bees into these two stalls. But unfortunately, the gates that I had to lock the bees in place interfered with the navigation, and I didn't have time to debug it, so I had to go without that feature. As you can see, the soldiers were notified where I was, and now they're chasing me. So that should give you a pretty good idea of how the bees operate. So let's come over here and look at the code. So the first thing is we are going to pull up navigation. So over here in the navigation creator, this is just a class. We have our navigation node, which contains. I tried using Unity's physics class for updating traversable nodes. However, there's a bunch of issues with colliders that are in the area of, if a ray originates within a collider, regardless of whether or not it's the game object that is casting the ray or not, it doesn't return it. So instead of doing that, I opted to use colliders and toggle them on and off. This IE enumerator check geometry. It disables. It sees if any obstacle was recorded, and then sets traversable. Resets the obstacle to null, and then deactivates the game object, so that we're not eating up CPU cycles. And it stores an array of links. Rather than using a list and storing every possible node that you get to, I went with adjacent nodes only. So over here in the navigation creator, what we're doing right here is we are creating all of the nodes, all the navigation nodes, and we're going across the x-axis first, and then starting back to the left and moving forward along the z-axis based off of some values that are fed into it from the navigation script. And then down here we are adding in links. So this is the navigation script. This min x, max x, those represent the minimum and maximum x values where nodes can be placed. The min z and max z represent the minimum and maximum z values where nodes can be placed. And then we have this float node spacing, which is the gap between the nodes. And then I have this, the rest of these variables right here are actually just for debugging, as well as the path. So the way this works is pretty much the same way that A* worked in my project from 3 weeks ago in week 2, with the exception of I'm not using a graph. Rather than using a graph, I'm going through this nodes list and accessing the links as I'm iterating through. So as soon as we start, we go ahead and we create the navigation structure, and then in our get path, this is the A* algorithm right here. So what we're going to do is we are going to feed it in a list by reference, the index of the start node and the index of the finish node. We are going to start with the start node, and we're going to place that into the open set. Then we enter our do while loop, where we pull the first node from the open set and place it in the closed set, and then we update our total cost. From that, we create a vertex. If the vertex we just placed into the closed set is the finish node, then we're done and we're going to break out of this loop. If not, we are going to iterate through all of the links in the navigation node's links array. And if the link is null, because they can have up to 8 nodes listed, but they won't always have 8 nodes. So if the link is null or the link is not traversable, we're going to skip it. If that's not the case, we'll make a vertex to hold all the information. If it's not in the closed set, we're going to check the open set. If it's not in the open set, we're going to go ahead and set our F, G, and H values and set the parent to the vertex that we created before we entered the for each loop. If it's already in the open set, we're just going to update the parent G, F, and H values down here. Once we've finished iterating through the links, through all of the links in the node's links array, we are going to find the next vertex in the open set that we can pull. Now, if if at any point in time we return -1 from this function right here, this get next open set index, that means that no path is found, so we're going to break out of the loop and return false. As long as we haven't found the finish, and we don't, and we are still finding vertices in the open set, we'll continue doing this. As soon as we get done with that, we are going to come down here. We are going to compile the path by tracing the parents back to the start. Once we've done that, we're actually feeding these into the list we passed in by reference up here. So once we do that, we will return true, and the path will be ready to go. Now for the h value, for the heuristic, we're using square Euclidean distance. All of distances in this are square distance. So this one's square Euclidean distance. And then you can see right here we have our update traversable, which is an IE numerator, and we yield for 1 frame until we run it again. Right now it's set for every 100 nodes. So that's navigation. The next thing we have is we have our game manager. As you can see right here, we have a finite state machine. And all this does is we have a timer up here, which is the day-night cycle. So when time is up and it's time to switch between day and night, we are going to reset the timer. We're going to set day to whatever it is. And then we're going to broadcast an event to all the registered receivers for the day-night change, for the day-night change event. And that happens over here in the Hive. This is an updated version of the Hive to, previously I was narrowcasting this new flower notification. Now it's being broadcast because it's cleaner that way. And then we've added our day-night notification to it. And we've added some additional functionality to so we can access the navigation through our Hive. So the bees only access the Hive for any information. All information is routed through the Hive. So we have our get get closest node, which is used when they're trying to pick out a valid position to move to, and they don't need a path for it. Then we have the get path, which calls the get path function from the navigation script. And then we have our broadcast functions down here. The notify soldiers, panic, and panic are left over. The time change right here is new, so that way the bees can react to the day-night cycle. So coming over to the actual bees, before I get too deeply involved into the code, we're going to pull up these two finite state machines right here. So we have our bee sleep and our bee panic. So the bee sleep, what we're going to do is it starts in this onBehavior start. So we're going to set a position, and then we're going to set our state to go to bed. You'll notice that there is no update function and there's no start function in this. All of that is handled from the decision tree. So this is just the finite state machine. This is just the functionality to carry out the sleep behavior. So we start off here. We're going to set a target position, and then we are going to change our state to go to bed. While we're in the go to bed, we are going to move towards the hive, and we're going to respond to signals. So the only signal that we're interested while the bee is going to bed is a touch signal from the hive. Once it gets to the hive, while it's in this particular behavior, it's going to turn off the mesh renderers and turn off the collider to simulate sleep. We're going to set our sleeping variable in the new B data script to true, and we're going to set our state to sleep, which is just an empty state. And I will illustrate how that works in just a moment. Now over here in the B panic, I've reworked this the point that they're going to flee to take advantage of the fact that I have direct access to the navigation structure, unlike when I was using Unity's nav mesh. So we are going to select a random point on the map. We are going to find the closest node to that, and as long as that node is greater, as long as the distance to that node is greater than the panic distance away from the player, we're going to move to that point. So that provides a lot more variety. Instead of them all being lined up and looking stupid, this looks more realistic. They scatter all over the place. Once we've done that, we're going to switch to runaway, which just moves the bee to the point, and when they get there, they are going to cower in fear still. When they're done cowering in fear, what they're going to do is they're going to set the panicking variable in the data script to false, and they're going to change their target position to their secondary target position. And then what we have down here is our movement code. So what we're going to do is to move the bee, what we're doing here is we're casting a ray to see if there's obstacles in the way. If there are obstacles in the way, we're going to navigate those by pulling a path, by getting a path around the obstacle from our navigation, from the navigation script. Once we're clear of the obstacle, we will switch back to straight line navigation. Okay, so now that we've covered those two scripts, we can cover the decision trees. Now, all of the decision trees right now, they're identical. The difference being the specific values that are stored in the work variable right here. So for the scout, we're storing the scout B 2.0 script. For the worker B, we're storing the worker B 2.0 script, and for the soldier B, it's the soldier B 2.0 script. So since all of the decision trees are the same, with the exception of that one particular variable, I'm just going to walk through one of these, and then I'll illustrate the actual, the individual behavior scripts. So what we're doing right here, once we initialize, we always start, the default state is always working. So for soldiers, they're going to be running their soldiers, the soldier behavior. For the workers, it's going to be the default working behavior, and for the scouts, it's the default scouting behavior. But in the update function, we have a decision tree. So the way this works is the default state is working. However, if we get a panic notification, we're going to set the panicking variable from the B data script to true, and that's going to trigger these two branches right here. So if we're panicking, and so if that gets set to true and we're not already panicking, we're going to see if the bee is sleeping. If the bee is sleeping, we are going to ignore the panic notification and continue sleeping. If the bee is not sleeping, the bee is going to panic, and we're going to switch to the panic behavior. Now, to ensure that we don't switch from the panicking state to the working state, to ensure that we don't have any funny behavior, I've included this right here. So if we're panicking, so if this is false but panicking is still true, we're going to come down here. We're just not going to do anything. Now this second branch deals with the day-night cycles. So we receive a day-night notification that sets our time change variable up here to true. So if that's the case, we are going to determine if the bee is sleeping and it's daytime, we're going to have the bee wake up. Otherwise, if the bee is not sleeping and it is nighttime and the bee's not already sleeping for some reason, or sorry, we haven't already transitioned to the sleeping behavior, then we're going to transition to the sleeping behavior. And if neither of these is the case, we're going to ignore the time change notification. Now this last branch, it might look a little bit confusing, but what we're checking right here is we're seeing, so if the bee is not sleeping and it's daytime and the bee is not already working, we're going to have the bee start working. If it's daytime and the bee's not panicking and the bee's not already working, then we're going to have the bee start working. So this is what allows us to transition from the panic finite state machine and the sleep finite state machine to the working finite state machine. So if we come over here, this is the soldier finite state machine right here. So we always start off on the on behavior start, which is going to set a patrol position, and we're going to start patrolling. So if we scroll all the way down here, here is our set patrol position. What we're going to do is we're going to select a random point within a specified range. And then we are going to find the closest navigation node to that. We're going to calculate a path to get there. And we are going to assign the first node from that path to our target position. Up here in the patrol, we are also going to set our secondary target to this endpoint. So up here in the patrol, we are going to check to see if we have reached our secondary target. If we haven't, if we've reached our secondary target, we're going to set a timer, and we're going to sit there for a couple of seconds. If we haven't reached our secondary target, which is the endpoint for the path we calculated, we are going to determine if we've reached the next point on the path. And if we have, we are going to update the target position so that we can move to the next point. Once we get to chase, before we talk about chase, we'll talk about the signals. I've left the signal selection the same as it was. So for soldiers, we're only interested in player signals, touch, sound, and sight. And if they see any of those, if the soldier touches the player, it's going to kill them. If it hears or sees the player, it's going to set the target position to the location where the signal originated from. In both cases, and it's going to switch behaviors to state, or to chase, I mean. So down here, we are going to determine if we've reached the point of the signal. If we haven't, if we have, and we haven't set a reset timer, we're going to set that. If we've already set the reset timer, and time has expired, we're going to go back patrolling. As long as that's not the case, we are going to continue moving towards the target position. Now, to ensure that this respond to signal right here that we're calling right there, and as part of patrol, this ensures that we are always processing our signals. And then this stuck is included to handle the gates that I didn't get to demonstrate. If there's no path found, they'll enter the stuck state, and then every so often they will check to see if they can get to where they're going, if a path exists to get to where they're going. So moving on to the Scout Bee. The Scout's sole job is to scout for flowers. It can remember where 3 flowers are. When it transitions, this on behavior start, if it went to sleep or if it was panicking and it's already recorded flowers, when we switch back to working, we're going to go ahead and have the bee report its findings to the hive. Otherwise, we're just going to have it start searching right away from where it's at. When we process our sense signals, we're going to select them based on an order of precedence: touch, sound, player-sided, and other-sided, right here. And then we have some transitions up here. So specifically, the hive. If the scout is reporting and it touches the hive, it's going to report its findings to the hive. It's going to set a new search position, and it's going to transition to searching. If it hears the player, it's just going to notify the soldiers and continue on doing what it's doing. And if it touches the player, it's going to panic and notify the soldiers. If it touches a flower and the flower is not in its, memory banks yet, it's going to record the flower's position. Now, if it hears the player, it's just going to notify the soldiers. And if it sees the player, again, it's just going to notify the soldiers. If it sees a flower and the flower has not been added to its memory yet, and it can still hold more, it will add that to. It will remember where that flower is. So when we come down here, we have our search. Now this right here is how we continue moving around the map. So what we're going to do is, in our set search position, we're going to pick a random point. We're going to find the node that's closest. We're going to pick a random node, a random traversable node, and then we are going to get a path to that node. And then we're going to follow that path up here with the move. Now, if at any point in time our flower count is greater than or equal to the max flower count, or enough time has expired, we're going to switch to reporting. And when we go to report, all we're going to do is respond to signals and continue moving towards the hive. And then stuck is the same as it was for the soldiers. Now for the move, move is a lot simpler down here because we're always using a path for the scouts. So we're always, so if we haven't reached the target position yet, we're going to get the next point. Or sorry, if we've reached the next point on the path, we're going to update that, and if not, we're going to continue moving. The last one is the worker. So the worker is always going to start off by delivering. So it's going to go to the hive and see if it's going to deliver a flower if it is transitioning from panic or sleep. And if it's just starting off, it's just going to go to the hive and wait for flower locations. If we come down here, this is the most complex response to signals. So we're interested in, our selection is the same as it was for the scouts. Touch, sound, player-sided, other-sided. So if we touch the hive and we're delivering, we are going to remove the flower that we gathered from the hive's flower list, and we're going to try and get a new flower position. If a new flower position is available, we're going to get a path to the new flower location and switch over to gathering. If not, we're going to have the bee remain idle until new flower locations become available. If it's the player, if the bee touches the player, then the bee is going to panic, notify the soldiers, and once it panics, it will switch out of this behavior and move over to the panic behavior. And if it touches a flower, if it hasn't gathered a flower, it's going to gather that flower, and it's going to calculate a path back to the hive and go there to deliver it. Now, if the worker bee hears the player, it's going to panic. It's going to notify the soldiers, and that'll end up it'll end up out of this behavior tree and into the panic tree. If it sees the player, it's the same thing. It's going to panic and notify the soldiers. If it sees a flower and it hasn't gathered a flower yet, then it's going to move to that flower. It's going to change its target position to the flower and go there so it can gather it. So here in our gather state, I've added some more control over what it used to be. So if we haven't reached our secondary target, which is the position reported to us by the hive, we are going to continue moving along our path, and the movement code is the same as it was for the scouts. The worker bees always use paths. They're never moving towards. They're never chasing the player around, so they're always using paths that are returned from the A star function. So if we haven't reached our final destination, we're going to continue moving. If we have, if we've reached our final destination and a flower touch signal has not triggered, then obviously the flower is not there, so we're going to return to the hive. And then for deliver, we're just going to respond to signals and continue to move to the hive, because the transition out of deliver is set up right here in the respond to signals, where we're going to transition to either gathering or idling after we've reached the hive. And then in idle, the new flower notification, we're using a Boolean variable up here in the script, flower locations available. So the idle is no longer an empty script. Instead, we're going to respond to signals, and if new flower locations become available, we're going to calculate a path to the hive and switch states to delivering. And by doing that, it will automatically, as soon as we get that touch event from the hive, the bee will ask for a new flower location. So the very last thing is I added movement code. So what we're doing right here is we're going to always, if we're not facing the the position we're moving to, we are going to move to it by calculating a rotation down here in our turn towards, which returns a bool. So we only have to call this if the rotation is not set. And then our move is just a simple move where we're going to move directly towards the target position. So the last thing is the B data. This is just updated variables. Rather than handling parsing in the finite state machines, parsing through the signals is now done through the B data script. And that covers all of the new code that was implemented for this project. If you have any questions about the differences between this project and the original project, you can watch the week 3 video. And if you have any other questions, feel free to ask. Thanks for watching.